properties are lemniscate star likeness and exponential star likeness of regular column wave function. My presentation consists of two sections and references. In the first section, I will mention about some basics in geometric function theory, and I will give the definition of regular column wave function. I will present its some properties. In the second section, I will mention about my main results. Let R, C, and Z plus denote the sets of real numbers, complex numbers, and positive integers, respectively. By H, A, and V denote the class of all analytic functions defined in the open unit disk D of the form 1. Let A be the subclass of H01 consisting of functions f normalized by the condition f0 equal to 0 and f derivative 0 equal to 1, and set H11 equal to H1. Now I want to give the definition of univalent function. A function fz is said to be univalent in a domain B if the conditions fz1 equal to fz2 imply that z1 equal to z2. This is similar to one-to-one function. By S, we mean the class of functions belonging to A which are univalent in the open unit disk D. Now I want to give a definition star-like function. A set P in the complex plane is said to be star-like with respect to point W0 if the linear segment joining W0 to every other point W lies entirely in the domain B. If a function f maps the unit disk D onto a star-like domain with respect to W0, then we say that the function f is star-like with respect to W0. In the special case that W0 equal to 0, we say that the function f is star-like function simply. Let's alpha satisfy this condition. By S star alpha, we denote subclass of A consisting of functions which are star-like of order alpha. The analytic characterization of star-like functions of order alpha can be given to equality 2. I would like to emphasize here that the class S star is subset of the class S. For the analytic function f and g in the unit disk D, the function f is said to be subordinate to function g if there exists a function omega analytic in D with W0 and equal to 0 and modulus of WZ is smaller than unit, and such that fz equal to g wz. F g is univalent function, then f is subordinate to function g if and only if f0 equal to g0 and fd is subset of gd. In the literature, there is a class of functions S star phi introduced by Ma and Minda, and it is known as Ma-Minda star-like functions. Here, the function phi is analytic and univalent on the unit disk, for which the function phi is star-like with respect to unit, and it is symmetric about real axis with the derivative of the function is positive. By the particular choosing of the function phi, many subclasses of star-like functions were defined in the literature. For example, by taking the function phi like this, we obtain the class S star AB, and it is called the class of Janowski star-like functions. And by taking A and B like this, the class S star alpha is known as star-like functions of order alpha, and it was introduced by Robertson. In this class, setting alpha equal to 0, we obtain the class of star-like functions given by 2. Also, by taking the function phi like this, Sokol and Stankiewicz introduced the class SL. This class is known as lemniscate star-like function class. In terms of subordination principle, the function f is called lemniscate star-like if condition 4 holds. On the other hand, by taking subordinate function exponential z, Bendratta et al. Defined the class S star E of star-like functions associated with the exponential function satisfying condition 5. This function class is known as exponential star-like function class. Now, I would like to remind the basics of differential subordination principle. Let Q denote the sets of analytic and univalent function Q in the closure D minus EQ, where EQ is like this, and such that the derivative of Q is not equal to 0 for zeta. The definition 3 is that let omega be a set in complex plane, Q is in this set, and n is a natural number or positive integer. The class of admissible functions psi n consists of those functions psi that satisfy the admissibility condition 6 whenever R, S, and other parameters satisfy these conditions. We write psi 1 equal to psi simply. Lemma 1 is known as differential subordination principle. Let psi in big psi n with Q0 equal to A is a complex number. If the function P in the class H an satisfies these conditions, then we say that the function P is subordinate to function Q. Very recently, many authors, by taking different functions instead of above functions, they gave some particular case of above lemma. For example, by taking function Qz equal to square root 1 minus z, Madan et al. Gave the following lemma. According to this lemma, under these conditions, if the function psi in this omega is in omega, then the function P is subordinate this function. This function is related with the lemniscate of Bernoulli. Because of this function class is known as lemniscate star-like function class. Here, it is worth to mention that in the case of the first order differential subordination, the above admissibility condition, that is this, reduces to this. Also, Naz et al. Studied about the class of admissible function associated with the exponential function, taking the subordinate function as exponential functions. They gave another special case of lemma 1 as follows. Let omega be a subset of complex plane and the function psi satisfies these conditions. This condition is admissibility condition. Whenever R, S, and other parameters satisfies these conditions. If the function P is analytic function in D with P0 equal to 1 and the function psi in this set, then the function Pz is subordinate the function E power z. This function class is known as exponential star-like function class. It is important to emphasize here that the admissibility condition, this admissibility condition is verified for all R, S, and other parameters. Also, for the case the function psi is defined like this, the admissibility condition reduces to this. Now I want to give the definition of regular column wave function and its some properties.
Can you
İbrahim Hocam, you have 3 minutes left.
Okay,
And then 2 minutes for questions.
Okay. The following second order differential equation is known as Coulomb differential equation, and it has a series representation like this. By using the Weierstrass-Jan canonical, by using Hadamard product representation, we can write that the function f il eta can be written as an infinite product like this. The function f il eta does not belong to class A. We consider this form. This form is known as normalized Coulomb wave function. Now I will present my main results. Theorem 1 is that let eta and L are complex number. If the inequality 11 holds, then the normalized regular Coulomb wave function G L eta is lemniscate star-like in the unit disk. In order to prove this assertion, we will use the lemma 2 given by Madan et al., but I will omit the details. Details here. We know that there is a close relationship Coulomb wave function and classical Bessel function of the first kind. In the above theorem, by taking eta equal to 0, we obtain that the function f il 0 equal to this. This is a classical Bessel function. Also, by using Legendre duplication formula for Euler's gamma function, we can write that this equality holds. By using the above equalities, we have the following corollary. Let L is a complex number. If this inequality holds, then the normalized Bessel function of the first kind is lemniscate star-like in the unit disk. Also, my second result is that let eta and L are a complex number. If the inequality 27 holds, then the normalized regular Coulomb wave function GL eta is exponential star-like in the unit disk. This assertion can be proven by using lemma 3 due to Naz et al. Again, by using similar things, we can give the following corollary for Bessel functions.
Ibrahim Hocam, your time is over.
Okay, my references here. Thank you for your attention.
Thank you very much. Is there any question? I think there is no question. So another presenter is Onur Şahin, and his title of speech, a perturbation procedure for a multi-component beam with high construct properties in case of lowest vibration modes. And I will give you word, Onur Hocam. Onur Şahin.
Thank you. 1 second, please. Hello, my name is Onur Şahin. Today I'm going to talk about a perturbation procedure for a multi-component beam with high contrast properties in case of lowest vibration modes. First, I would like to say something about why we consider this problem. As known, dynamics of inhomogeneous elastic solids is an important research area due to its numerical applications in modern industries. Among the latest technological developments, composite materials have received an increasing amount of attention in various fields of civil and mechanical engineering. Laminated glass beams and plates, photovoltaic panels, and functionally graded materials can be given as examples. Composite beam structures are also connected with soft robotics, which use deformable materials to construct compliance systems. Metamaterials which are employed considerably in engineering with recent technological developments may be given as another example for multi-layer structures. And what are the advantages of using a perturbation procedure? why we will develop a perturbation procedure for such problems. It's clear that the exact formulation of eigenfrequencies and eigenforms of inhomogeneous structures are generally given by sophisticated transcendental relations. Therefore, the exact analysis of such problems is quite restrictive. Developed a perturbation procedure in order to investigate near zero frequencies and corresponding displacements enables to further mathematical and physical analysis. If the eigenfrequencies and eigenforms of such problems were calculated by the numerical procedure, such as finite element method, there would be limited potentials for physical insight. So all these results motivate us to develop a perturbation procedure for the following problems. Let's now state the problem. We consider a multi-component elastic beam comprised of a finite number of alternating stiff and soft components of arbitrary lengths Li. Here, the black rectangles show the stiff components of the beam, and the white rectangle correspond to soft components of the beam. And for this problem, all the stiff components have same material properties. Namely, all the stiff components have same Young moduli A1 and same material density ρ1. Similarly, all the soft components again have same Young modulus A2 and material density ρ2. And it can be seen from figure 1, the first and the last components of the beam are assumed to be stiff. And the equation of time harmonic motion for each component are given by this fourth order differential equation. Here, Ui are displacements, omega is the vibration frequency, and Am is given by this relation. Here, in this relation, I is the moment of inertia, and A is the cross-sectional area of the beam. And for this beam, the displacements, stresses, bending moments, and shear forces must be continuous at all interfaces, which are formulated by these equations. Here, epsilon is defined by A2 over A1, and because of the high contrast properties in soft and stiff components of the beam, epsilon become a small parameter. And also here, chi I is defined by the sum of the length of the components of the beam. For this problem, we consider a free end condition, which is formulated by these two equations. Let's now introduce local dimensionless coordinates and scaled frequencies by Ci and lambda I. It can be seen from the definition of the scaled frequencies that the frequencies of soft and stiff components are related to each other through this equation. We also introduce dimensionless quantities Hi such that Xi are lying between Hi and Hi plus 1. Thus, the equations of motion in the dimensionless form are given by again a fourth order differential equation with boundary conditions, with continuity conditions and boundary conditions. It's the formulation of our problem. We now present a global low frequency perturbation scheme. Now we study the lowest eigenmodes of multi-component beam using a perturbation techniques earlier developed for longitudinal vibrations of strongly inhomogeneous rods. Here we restrict our attention to global low frequency regime, which can be formulated by this asymptotic relation. And because of the global low frequency regime, the ratio of densities of stiff and soft components is also assumed to be small, namely ρ1 over ρ2 is order of epsilon. Let's now expand frequencies and displacements into the following asymptotic series. And on substituting these asymptotic series into the equations of motion, we, at the leading order, we have a fourth order homogeneous differential equation for all components of the beam. Now we focus on stiff components first. Similarly, the boundary and continuity conditions at the leading order can be written by these equations. Thus, we have a boundary value problem given by the governing equation and leading stiff continuity conditions. The solution of this boundary value problem given by this linear function, which correspond to rigid body motions, including both translations and rotations. And leading order displacements of the soft components are again governed by the same leading governing equation and the following equations, four equations, which are obtained from the continuity conditions. And therefore, the displacements of the soft components can be found by the following third degree polynomial of Xi. The constants appearing in the solution of the soft and stiff displacements are related to each other by this equation. Here, Pi is a matrix given in the appendix. We now proceed to next order problem. Similar to the leading order problem, the next order problem for the stiff component is given by, again, a fourth order equation with the continuity and boundary condition. First, using the leading order displacements for the soft components, the continuity conditions, the next order continuity conditions take the following form. And then substituting the expression for leading order displacement for stiff component into the next order governing equation and integrating with respect to Xi over the interval.
Sorry, Onur Hocam, you have 2 minutes to sum up because we have a question session. So okay. Can you sum up your presentation?
Yeah, okay.
Sorry, thank you.
If we take the integral of this governing equation, we have a equation for lambda I, and then multiplying the governing equation by Xi I and integrating again over the same interval, we have another equation. Using the relation between the constants, these two equations turns to these two equations, and following a similar procedure for the left and right outer components of the beam, we again have the two equations for frequency of the stiff parts of the beam. Thus, we have obtained n+1 equations in AI and BI. Solvability of this linear algebraic system gives the frequency equation of the considered problem. We note that a similar algebraic system has been obtained for the multi-component rod in the reference 2. However, the dimension was twice less due to only translation rigid body motion possible for the rod. Here we give an example. We considered a 5-component beam with 3 ends. Taking into consideration n equals 5 in the above formula, it gives us these 6 equations. And from here, using the relation between the frequencies, we obtain the equation, and the eigenfrequencies can be obtained from the solution of this equation. Here we present some figures, including numerical comparison of the exact and asymptotic results. Exact and asymptotic curves of the frequency equation for the 5-component beam. it can be easily seen that as the small parameter epsilon becomes smaller, which means that there would be a great contrast between the stiff and soft components. The exact curves, the exact solution become highly compatible with the asymptotic one. And here the exact asymptotic displacements are demonstrated for the corresponding frequencies, and it can be again easily seen from all these figures that the exact displacements present a quite good approximation to the asymptotic this solution present a quite good approximation to the exact one. And here are conclusions. I'm skipping all of that and our appendix and references. Thank you for your attention.
Yeah. Any question? So, no one? So, I have a question. Then.
Yeah.
So, have you tried to epsilon like 10 to minus 5 or 6 for too small epsilon? Did you?
Yeah, here we consider epsilon is 0.01.
So 10 to minus 2.
Sorry?
10 to minus 2, right?
Yes.
Yeah. How about smaller than this one?
So for this small, for
Mm-hmm.
this small epsilon, it's still give a quite good approximation. If we consider a smaller one, they become very. Probably it will give very good approximation. They will be matched.
Because my question is, many application requires the much smaller epsilon, I think.
But, yes, but our
yeah, go ahead.
Our perturbation method is depending on the small parameter. If we consider smaller epsilon, it gives us a very good approximation. But if you ask what will be if we take a big epsilon, like 1/10, then this approximation would not be very good. But for the smaller one, it will give a good approximation.
Okay. Thank you. Thank you for your presentation.
Thank you very much.
Okay, the next presenter will be the I will try to spell the correct one. Chapan Namishe. Is that correct? Chapan or Chaban? Is he or she here? Oh, he's not here, right? Okay, I think she or he, I don't know, is not here. How about Ali? Look, Mr. Ali? Yeah.
Yeah, I am here.
Okay. Go ahead, because the previous one is absent.
Okay.
So your presentation will be on the solution of two praise and one predator type model approached by the Banach fixed point.
Yeah. I will share my screen first. Can you allow me to share my screen?
Yeah, sure. Sure, take your time. But
you can share your screen, it's allowed.
I am unable to share my screen. Can you please allow me to share so that I can share my screen?
We allowed you.
Okay.
yeah.
Allowed.
Do you have
But it's a error.
any question on the share?
Yeah, it's a error.
We can help you if you want.
Okay, so if you have my slides, so I can follow from here
Yeah.
because I am unable to share my
Oh,
screen.
okay. Elif hocam.
Okay, so now I can share. It's okay.
Okay. Okay. Go ahead.
So can you share my can you see my screen now?
No, just see you.
Okay, now is it okay?
I don't think so.
So can I start?
So what we need to do is click on the share screen and then
Yeah.
your document.
Okay, share screen.
Elif hocam, can you do this?
No, actually it's a error.
Sorry?
It's a error. I cannot share
It
my
says
screen.
error?
Yeah.
Oh, I don't know.
I don't know why but do you have my slides? I already sent it to you.
You can send your slides, this email.
Yeah.
I write from chat.
Oh. What? Which one did you send?
I already
me?
sent it to you, I think.
Oh, I don't know.
I sent my email to you.
Okay, so I am sending to the email. Okay.
Email? Okay, I'll check my email.
Just a moment.
No, I don't have one.
What?
جيبي لي كي ترتاح شوفي يعاوني شو الصوت.
So Elif hocam, can you help him?
Yeah. Okay. So I already sent it to you.
To whom?
Alif.
Oh, okay. Okay.
جبتي له ها؟ ديك خطرات تسقسي تساعد على البارت باكاج. وينه نقول لك وينه؟ مادام لا في بالها ذوك عطيها لها ذوك. سقسي تساعد ديك خطرة على البارت باكاج تاع راك في الفوق. أنا سمعت شفت لقيته. وين؟ قال لي شوف لنا نساعدك فيه. لا نتاعك ما فيهاش الحديدات هذيك اللي يلصقوا فيها. هو يدير 1450 ياك؟ والحديدات يدير 650.
Okay, Dr. Ali, so you click on share screen and then, oh, okay, also, okay, now it's good, yes.
Yeah. You can you open it in a full, yeah, okay.
It's okay.
Now it's good.
Yeah, from the first.
Okay, go ahead and take your time.
Okay. Yeah, it is okay. So you can start from the first page. No, start from the first page, first slide. Yeah.
This is your first page, table of contents.
No, previous.
Another page?
Okay.
This page?
No, actually first one, this is fourth. From the beginning, yeah.
It's okay?
Yeah, okay. Okay, I am Ali Turab from Department of Mathematics and Statistics, Thammasat University, Thailand. The title of my presentation is on the solution of the two-phase and one-predator type model approached by the Banach fixed-point theorem. So I have divided my presentation into the following parts. First of all, I will talk about the motivation of my talk, and then I will discuss about some definitions and theorems which are helpful to prove our main result. Then I will move to the main result. Main result consists of one main theorem And then in the end, I will discuss about one example which shows the purity and significance of our result in this direction. So let's begin with the first section, which is motivation. I'll start with this section with the famous quotation of American sociologist Martha Beck. She said that every day brings new choices. It means that, next slide, please. It means that life is made up of an infinite number of choices, and each choice we choose, it will be helpful it will be helpful in our life. For example, when we follow a path, there are many choices to choose a suitable path. When we follow, for example, when we follow some direction in a Google Map even shows some direction, 2 or 3 direction, and it shows that which direction is more faster than the other one. So we pick a more suitable choice among them. So it means that we have to tackle a lot of choices in our life. For example, like we have a lot of shoes, so we can pick any of them. So it means that we have many choices, even in the colors form as well. And each person has different choices. For example, if I like red color, or maybe the other person like different color like black. So it means that choices are different, differ from person to person. It's up to the person, personal choices. Next, please. Even this phenomena also exists in the life of animals as well. Like we can see in the animal's life, animals also have the choices. For example, in the following picture, you can see that a lion has 2 choices to eat. So it means that when a lion has 2 choices, so he has to pick a more suitable one for himself. So it means that in this picture, you can see that a lion acts as a predator, and a cow and the cows are act as a prey. So it means that when a lion and when a predator has 2 choices, so which choice he will choose or he will attract towards it. So this is called the predator and prey type model in a psychological form. So next, please. In the last year, we will discuss such type of phenomena in terms of a fish. And when a fish is put in a fish tank, and we have to observe the behavior of a fish when a fish is given 2 choices to swim. For example, in the following picture, a fish has 2 choices, whether the fish move towards box A or towards box B. And we have to describe such type of behavior with the following functional equation, which is in the red box. And such type of functional equation describe the behavior of animals when they have 2 choices with its corresponding probabilities x and 1 minus x. So, and where alpha and beta are in between 0 and 1, and f of 0 equal to 0 and f of 1 equal to 1 are the boundary condition for such type of models. Our aim is to generalize such type of models and discuss a general model and find the existence and uniqueness of such type of model when a predator has 2 choices. This is our aim. So let's move to the next section, which is preliminaries. In this section, we will talk about the basic definitions of our technique. Our technique, we use fixed point theory. So the first question is, what is a fixed point? Actually, there are many definitions of fixed point. The most simplest one is a point which is mapped to itself is called a fixed point. In mathematical form, we can say that if we have 2 non-empty sets like x and y, and we have a mapping from x to y, then we can say that a point from the domain is called a fixed point of a mapping T if and only if x equal to Tx. It means that a point mapped to itself is called a fixed point. The next definition is about the contraction mapping, which is most important part in our main theorem. We say that let XD be a metric space, and we have a self-mapping from x to x, and we satisfy such type of condition with a constant contractive coefficient k, which is strictly less than 1. It's called a contraction mapping. So please next page. Yeah. And then we have the example. We have E, which is in R, and we have the mapping from E to E, a self-mapping. And we define a mapping like x over 2 plus 1 over x. So we can see that with the usual metric space, T is a contraction mapping. It satisfies the contraction condition with a contractive coefficient 1 over 2. And then we, the main thing, okay, down please. Yeah, okay. The main theorem is about the Banach fixed point theorem. This is our technique in fixed point theory. In metric fixed point theory, this result is the most useful result because of its application. It says that if we need a complete metric space and we have a self-mapping and our self-mapping satisfies the contraction condition with a contractive coefficient strictly less than 1, then our mapping has then T has a unique fixed point. It means that we have a unique solution. Our aim is to apply such type of theorem to our functional equation and find the existence and uniqueness of the theorem. So let's move to the main result. Before moving to, down please. Before moving to the main theorem, we need some technical results. Like for example, we need to define a space. So let X be the collection of all continuous real value function from 0, 1 to R, such that phi of 0 equal to 0 and condition 1.1 holds. And we define a norm on such type of functions in like 1.2. Then with our space with such type of norm is a Banach space. So next, please. Yeah. So we shall be interested with the existence of the solution of the following functional equation, which is in 1.3, in which phi is a real value function and sigma 1 and sigma 2 are contraction mappings. So if we take, for example, if we take sigma 1 equal to alpha x plus 1 minus alpha and sigma 2 equal to beta x, where alpha and beta are in 0, 1, then 1.3 reduced to the functional equation discussed above in the fish model. It means that 1.3 is more general than the previous functional equation existing in the literature. I already mentioned the paper in the downward thing, in the footnotes. So such type of functional equations are very important because it describes the behavior of an animal in a two-choice situation. Sigma 1 and sigma 2 are two choices. For example, in this case, phi is a predator, and sigma 1 and sigma 2 act as prey. So a predator has two choices with its corresponding probabilities x and 1 minus x. And we have to observe the behavior of a predator in such type of situation. So let's move to the main theorem, theorem 1.1. So we consider the functional equation 1.3 above and suppose that sigma 1 and sigma 2 from 0, 1 to 0, 1 are contraction mappings with contractive coefficient A and B respectively, such that sigma 2 of 0 equal to 0 and 2A plus 2B is less than 1. And there exists a point in 0, 1 such that sigma 1 of that point equal to sigma 2 of that point. Then 1.3 has a unique solution. Moreover, the sequence in X defined like this converge to the unique solution of 1.3. It means that we have to construct a sequence, and such type of sequence is called a Picard sequence. We have to construct a Picard sequence, and our sequence converge to the unique solution of this. So this is our main theorem. To support this theorem, I will show you one example to clear this result. Yeah. So let's move to the example. So we consider the following functional equation. For example, sigma x equal to x sigma plus 1 minus x sigma into 2x over 7. For all x belong to closed interval 0, 1, where sigma is real valued function which is unknown. If we set the mapping sigma 1 and sigma 2 by sigma 1 of x equal to x plus 1 over 7 and sigma 2 of x equal to 2x over 7, then our functional equation 1.5 reduced to the functional equation 1.3. Here, okay, now we have to apply theorem, our main theorem here on such type of function. Okay, stop, please stop.
Sorry, Dr. Ali. You have 3 minutes to complete because of the limited time.
Okay,
So,
no problem.
Thank you.
Yeah. Previous slide, please. Yeah, here. So we have to apply here our main theorem. So in our main theorem, the main ingredients are sigma 1 and sigma 2 must be contraction mapping. Here we can see that sigma 1 and sigma 2 are contraction mapping with the contractive coefficient 1/7 and 2/7 respectively. Another condition is sigma 2 into 0 equal to 0, which is clearly satisfies. And the next, another condition is there must be a point on which sigma 1 and sigma 2 have the same value. And you can see from the graph, now that point is 1. At 1, the value of sigma 1 and sigma 2 are same. So all the conditions of our main theorem are satisfied. So we can apply our main theorem on such type of functional equation. Again, next, please. So it means that from the previous theorem, our main theorem, our such type of functional equation 1.5 has a unique solution. And it means that we can construct a sequence. And for example, for initial approximations, sigma 0 into x equal to x, if we start from here, then we can calculate the value of sigma 1, sigma 2, and so on. And our sequence, such type of sequence converge to the solution of 1.5. So to conclude my talk, what we have done, in this slides, we have discussed a probabilistic predator-prey model in which a predator has 2 choices, and we have to observe the behavior of a predator in such type of situation. What we have done, we describe a functional we discuss a more general functional equation, and we use the Banach fixed point theorem to find out the existence and uniqueness of such type of model. To support our result, we also present one example. So thank you so much. And if you have any questions, so you can ask me.
Any question on this presentation? No one? Okay. I have a question now. Yeah. So what if you change the contraction on sigma 1 and sigma 2 by Lipschitz, or just continuous functions?
Yeah,
Still
you can
holds?
change it. Yeah, you can change it. But what about then? We have to check whether our functional equation has a unique solution or not. Because for the uniqueness, we need the Banach contraction principle.
Yes.
Yeah.
Yes. But you know, some other theorems like Mans or Schauder fixed point.
Schauder fixed point theorem. Yes. We can apply. We can apply Schauder fixed point theorem, but if we apply Schauder fixed point theorem, then we cannot guarantee the uniqueness of the theorem, because Schauder fixed point theorem. We just find the existence of the theorem, existence of the solution.
Yeah, but your iteration likes the Mans iteration. Did you hear that? Mans.
Yeah, I already heard. I already read about
your iteration is like a Mans iteration. That's my question.
No, it is like a Picard iteration. But
Mans iteration it's like a Mans iteration, because Picard is just the integration of some, I don't know, function. So that's my question is, you can change the contraction to Lipschitz or continuous function and
we can change it, but we have to check our conditions as well. Maybe we need to introduce new conditions to find out
maybe
the existence
you can
of the
use
solution.
Maybe other.
For example, if we change to contractive condition, which is more bigger than the contraction. So we can, if we change little bit, then we can find out the existence and uniqueness of the solution as well.
Right.
But we need to check, or we need to introduce more conditions as well.
Yeah. Thank you. Thank you.
Thank you.
So any question? No. Okay. So we will go up to next presentation by Ainura Paladova. Yeah. Investigating the shock control. Right. Yeah. Go ahead. It's your turn.
Hi everyone, welcome to my presentation. I am Aynura Paladova. I am PhD student at Top University of Economics and Technology. Oh, today I will my presentation title is investigating the stock control model of type SS with dependent component. We have done this study with my teachers Salih Tekin and Tahir Hanalioğlu. Just a moment.
You have problem?
Yeah. Yes.
What was the problem?
Just a moment. Will you see my presentation? Do you see my presentation?
Yes, yes, yes.
Okay, I am sorry. The outline of my presentation is as follows. I will begin with introduction and the literature, then graphical display of my process and mathematical construction of my process. You will see. Then I present to you my main results, and I will finish results and references. We use my presentation is about stochastic processes and its applications. We use stochastic processes. Stochastic processes used in inventory, queuing theory, stock control, reliability, stochastic finance, and mathematical issue, and the others files. In literature, there are many valuable studies about these topics. This topic, Nesterova and she's friends early studies this problem on probability characteristic of stock control level in the model of type SS. Then these studies continued with Kaniev and his friends. You see these studies in my presentation. These are a literature review. I have skipped this. This, but many of these studies is about a dependent component, a stochastic process with dependent component, independent component, dependent component, stochastic process with dependent component is studied Brown and Solomon's papers, Haniev's and Haniyev's papers, but there are a little studies in the literature about these topics. Here you see my sample trajectory of process xt. I have this xt. My main process, Xi and eta is a random variable, which is the main random variable in this study. Xi and eta random variable is dependent, and Xi is inter-arrival time. Eta is the amount of demand. I have amount of demand. Our process is continued tau bir. Then when we reach tau bir, our process is reached S level and continues as at the second part. Mathematical construction of my process xt. We have Xn and Etn random variable. It is this is defined on sigma f per probable sigma fp space. Xi and Xn and eta and random variables take only positive value, and we have assumed that the distribution of this random variable are known and is denoted as follows. In order to define our main process xt, we must define the following random variable eta n yn. Also random variables ne we must define. Using these random variables, we have construct our process as follows. Our goal is this study is to investigate the ergodicity of the process xt and obtain analytical and asymptotic results for ergodic distribution and moments of ergodic distributions. Firstly, we have investigated ergodicity of the process xt and obtained exact expression of the ergodic distribution. For this, we defined some notations. Here, A is Xibir, and this Xibir minus A. Then Xn is a Markov process. Xn is a Markov process, and our process xt equal Xn for these intervals. We have theorem 4.1. This theorem we have take from studied Haniyev 1980 Haniyev study. Suppose this theorem is about the ergodicity of xt and this relationship is about this relationship. We have used this result for our problems. Here, Qx is a ergodic distribution where Xi and eta random variables are independent. This is studied in paper Nesilova. Then by using this theorem 4.1, we have give our main results. For this, we must define some functions, ray of x as this, and this is the graphics of ray of x, and phi x. We defined phi over function in terms of ray function. After this, we have give our main results. This is the theorem 4.2 is about when the random variables x and eta are independent, then ergodic distribution of process xt as follows. This is a proof of our theorem, but I skipped this. But this is continued our proof. These formulas is in these formulas Cn and the eta are dependent and have generally distributed. This is one example about these main results. When the random variable eta n has exponential distribution with parameter lambda, the exact expression of the ergodic distribution can be write as follows.
Sorry, Aynur Hocam. You have 3 minutes to complete because of limited time. So, okay. Can you sum up your presentation?
Here are another main results: asymptotic expansion for the ergodic distribution. We should give some preposition in order to prove our main result. This proposition and the lemmas. Then our second main result, when the Cn and the eta n are linearly dependent, then the asymptotic expansion for the ergodic distribution is as follows. This is our proof. I skipped this. Then we have proof the weak convergence of the process xt. For this, we firstly defined standardized process vt and show here's its weak convergence. Here I show you. When VT, the standardization function VT, the ergodic distribution of the process VT is as follows, weak convergence as follows. By using this result, we can say that our main process VT, the ergodic distribution of our process xt weakly convergence, uniform distribution in the interval, in this interval. Then we have obtained exact and asymptotic result for the moment of the ergodic distribution. This is exact formulas of the process for the moment of the process, and this is a proof. Then we have get asymptotic results for the ergodic moments of the process. This is our results. This is proof. Then there are our references. Thanks. I have finished.
Okay, thank you. Any question on this presentation? No one? Okay. Thank you. Thank you for the presentation. The next one is mine. I will present some existence and unique solution to raise capital fractional boundary value problem with impulses. Okay. So I'll start with, okay, the title is existence and uniqueness to solution for higher order raised capital fractional boundary value problem with impulsive. So we will introduce the problem statement, fractional calculus, some useful lemma, and main results. So the problem is this. This is similar to ordinary differential equations, but we changed the derivative with the fractional one. Here we use the raised capital fractional derivative. Shortly, I'll define what this means. And we assume age is continuous and the fractional power is between 1 and 2. And we use the antiperiodic boundary conditions. So first we disguise the space by uniform mesh x not x1 and that's xr and xr plus 1 is equals the time step t or base time, and we have an impulse in equation. Just jump on each point inside of the interval 0 to t. So we define the jumps by delta u at xk point by this, and also we define the jump of the derivative of u at the point xk, and we show this by delta u prime. Here's the right hand side limit, and this is left hand side limit defined by this formula. So yeah, here's the definition of the raised capital fractional derivative of order nu or alpha. Most commonly used alpha, but I use nu. This is the definition of raised capital derivative. It has two properties. It presents the history and future. And this one. Yeah, this here's the missing, but sorry. It can be defined on based on the the capital derivative is the mean of the left plus the right capital fractional derivatives. And here's the left fraction, capital fractional derivative is this one, for order of nu, and the right capital derivative defined as for this formula. So we define the space of functions as U is continues on each subinterval and has a jump on each point inside of interval. This interval is just a jump, not infinite jumps. And we define the G plus as the interval minus this discrete point. This space is Banach space with the supremum norm. The supremum norm, and this is Banach space. So we have a solution now. We have a lemma. It shows the problem, the fractional or differential equation of order nu between 1, 2 is a unique solution, and it has the form of this. This is proved in a paper. I forgot to cite it. Sorry. Yeah, this is proved in paper. Yeah, and we use these tools to prove our existence and uniqueness theorem. Yes. Okay. The boundary value problem, we interested in this one. This, we call this equation 1. The equation 1 is has a solution if and only if it has an integral equation like this one. The proof is technical and it's a little bit bigger, so I skip it. But the main result I present here is using by Banach contraction map principle. So we define a operator from our space, function space to function space, and our main goal is to show that this operator f has a unique fixed point, and this fixed point is the solution of our problem. So we define the operator f as a solution of this problem. Clearly, this is fixed point of f. If we have a u, this must be the fixed point of the operator f. This is the main idea. So our theorem is this, but it has some assumption. Assumption 1 is the continuous function has Lipschitz constants, with Lipschitz constants L1. Assumption 2 is the functions ik and ik plus are also Lipschitz. And if we have this relation, I mean this quantity less than 1, then problem 1 has a unique solution on the interval J. So we will again saying we will show this by showing f is contraction mapping. Some algebraic manipulation shows that fu minus fv less than equal this quantity plus 1, this one, and we use here if the assumption on H is Lipschitz with Lipschitz constant L1. This comes up this here, and we calculate here as this. And then again, the UK and UK plus prime is also Lipschitz. So Lipschitz constants L2 and L3 here. So taking the norm, this supranorm, taking the supranorm on each side gives you this. So we take out this part and just computing this integral gives you RL this quantity. Okay, yeah, therefore we conclude this part. By assumption, this number, this is a real number, less than 1, we assume this, and this shows F's contraction. By Banach theorem, it should have a unique fixed point. This unique fixed point is solution of our problem. We have one application example. We take H to be this function and jump on it. We just take 1 point, 1 of 3, and we define the jump function as this one. And boundary condition is also antiperiodic boundary conditions. So here we show H is Lipschitz, and U plus, U prime is also Lipschitz. Yeah, H U bir minus H U2 is equals this number, this quantity, and some modification gives you this 8 minus x less than 1. This number is less than bigger than 7, and so this coefficient is less than 1/7. So we show H is Lipschitz. So the assumption 1 is fulfilled in theorem 4 with Lipschitz constants 1/7. Similarly, we can show that I and I prime is also Lipschitz. We show here I to be Lipschitz. Just algebraic equation with L2 1/2. So we show the assumption 2 in theorem 4 is satisfied with L1 1/2 and L3. We then calculate, well, what is, yeah, I think L3 is the same. So we calculate this number less than 1. So we conclude that our theorem says this problem, this example has a unique solution by, okay, yeah, I finished. Any question? No one? Okay, thank you. Thank you, patient. So we finished all the presentation. I think Chapan is here now. I think he's not. Okay. Okay, thank you. Again, thank your patient, and we finished our sessions.